Okay, ladies and gents, let's get going. Thanks everyone for coming. Today we have the pleasure of welcoming Dr. Bertus Smith from across the road, our colleagues at UJ. Bertus, who's somewhere behind me, is a senior lecturer at UJ, and he did his PhD and MSc at UJ. The MSc working on banded iron formations from the Pongola and the Wits, right? And for his PhD, he worked on geometallurgy of the Bushveld complex. But his real passion is early life and not geometallurgy, apparently. So we welcome Bertus. Thank you, Bertus, for coming to give this talk. And I've already seen that it has some fantastic imagery in it, so you can look forward to some really good tomographic images.
Okay, the green light is on, so I assume that means I can go. Hello, everybody. Thanks for coming to this talk. I think it was advertised a bit last minute, but the turnout's pretty decent, so thanks for attending. I got title shamed earlier this week by one of the people here at Wits who basically said I need to come up with shorter talk titles. So I'll take that into account. Maybe next time I'll just call it Cool Rocky Stuff or something. But anyway, I think the title is important because you have to say what rocks you're going to look at, you have to say what's the importance of it, and you have to also say, well, there's going to be some different data in this and some different imagery that is not that commonly used in this specific field of geology. So we're going to go very far back in time. But first I'll do some introduction because I guess this is a fairly general group of geologists, and maybe not everybody works on iron formations and all these things. So let's go with iron formations, very straightforward. It's a chemical sedimentary rock that's rich in iron. There we go. So, and granular iron formations is a subset of iron formations because they get classified in different ways. You get a stratigraphic classification for iron formations, meaning are they sitting in a typical passive margin environment, then we call them superior type. Are they sitting associated with volcaniclastics, then we call them algoma type. Or are they capping glacial dimictites, then we call them Ropiton type. And then you also get mineralogical classifications, like the iron can come as silicates, carbonates, or oxides. So we talk about mineralogical facies. In this case, we're talking more about the textural classification, meaning you get micritic iron formations, which is a chemical precipitate, very fine grained, very rich in chert, and very fine precipitates of magnetite, siderite, anchorite, things like that. And then we get the granular iron formations. They are essentially what people think were originally chemically precipitated muds, and then they get reworked in some sedimentary process. Usually by regression, sea level goes down. Sometimes it might be every now and again you get storm wave action reworking these things. But what's very interesting about the granular iron formations, they generally tend to be younger and they come in more prominently later with iron formations. So iron formations at peak distribution from 3.8 billion years, and you see more and more in the geological record up to about 1.9, and then it generally disappears until the Neoproterozoic. Now the granular iron formations really show a peak here towards 2.1 to 1.9 billion years ago. But I'm going to talk about a bit of an exception in this case. There's the top one right there, that's the Sokoman iron formation, probably the best known granular iron formation in the world. And here below is from South Africa, the Griquatown iron formation, which is generally micritic, but it has these reworked, sedimentary reworked layers in it. So it's got a fairly big granular iron formation component to it. Then we're going to talk about stromatolites, and most of you know what this is. It's biochemical accretionary structures, layered mounds, columns, and sheet-like sedimentary rocks. And these are general consensus is it's formed by the growth of bacteria, usually in fairly shallow marine environments. The shallower the environment, the broader they'll grow. The deeper the environment, the harder it gets to sunlight, the steeper they'll grow. And there's very well-known ones from South Africa over there, from the Campbell-Rand. Here, if you go out to Mulder's Drift, Cradle of Humankind, that rock, that's the Mulmani carbonate succession, which also contains these spectacular stromatolites. You also get them in iron-rich deposits in the Phanerozoic. Here's an example from Egypt. And here's modern stromatolites at Sharks Bay in Australia, where cyanobacteria is currently living in a shallow marine environment, producing oxygen, living in Australia, and seemingly being happy about it. Now let's go to the geological setting. So here we're going quite far back in time. We're going to the Mazon group. It's the upper part of the Pongola supergroup. The lower Pongola supergroup is the Nsuzi. There's a person here, Alan Wilson, who's done exhaustive work on the Nsuzi. So if you ever want to know more about that, read some of his papers, which is mostly a volcanic succession with some sedimentary units in between. But now when we move into the Mazon, this is a very unique succession. It almost perfectly correlates to the West Rand group in the Wits, which is the unit on which this university and UJ is also built. So they're stratigraphically identical. They were probably deposited at different parts of the same basin at the same time. And what's interesting about this is this is probably one of the oldest and most complete supracratonic successions on Earth. So this thing is depositing in a beautiful passive marine environment at a time when most of the Earth was still in more greenstone type environments where the tectonics was not as stable, smaller continental fragments. Here in the Wits and the Kaapval Craton, you already had a very well developed passive marine succession. And what's interesting as well, another thing that correlates perfectly are these iron-rich units, either magnetic mudstones or iron formations that perfectly correlate between the Mazon and the West Rand group. And these are also the oldest superior type iron formations in the world, where you see an iron formation sitting beautifully within a shale and the shale sitting beautifully within a sandstone with some conglomerates. So you see beautiful marine transgressive regressive sequences not really being interrupted by tectonics or volcanism. So the one we are dealing with here is the Conga formation, which sits a bit higher up in the Mazon. If you go to the base, for the students here who have mapped in white and Fulosi, that beautiful iron formation that outcrops there, that's the Azermain member of the Vlakhoek, or the Azermain iron formation of the Vlakhoek member. That's probably the oldest superior type iron formation in the world. If you go higher up, again, you get multiple iron-rich units. And here we're in the Conga. And what's interesting about the Conga, it contains the oldest granular iron formation we know of in the world's geological record. It's probably about 2.96 to 2.84 billion years old. We do not know of an older granular iron formation on Earth. It's also not very well developed, so it was easy to miss for a very long time. It's also not well preserved because it gets deposited in a fairly shallow environment. If you get a regression or erosion, you form an erosive unconformity, the first thing will be the shallower rocks. So you don't see it throughout the whole succession. It's fairly limited. Where we do know it occurs is if you go to the south of Swaziland, right there, you see it in field outcrop. And then what's fantastic is near Nongoma in South Africa, AngloGold Ashanti drilled a whole bunch of deep-level drill cores through the Mazon looking for gold. I don't think they found much gold, but if you combine those 4 or 5 drill cores, you get an almost complete record of the Mazon. And lo and behold, when we looked in the drill core at a depth of about 1.3 kilometers, we found that same granular iron formation sitting right there. It sits in 2 beds, and these beds are interbedded with iron-rich mudstone and macritic iron formation. So it's sitting in a very weird place that you wouldn't expect. But we think we've got a good reason why we see it where we see it. Now what's also nice is in drill core you don't see fantastic sedimentary structures, but because it's an outcrop, there you can go look at it in Swaziland, you can take pictures and you can see this thing is very rich with sedimentary structures. So for example, you see like hummocks and beautiful beds. You can see there was wave action interacting with these things. At least in this outcrop you can see that. You get low angle cross bedding as well, so some sort of directional flow, and you can see some of the silicified mud actually got ripped up as well. So probably storm waves interacted with this quite often. And if you look there, you can also, in outcrop, unfortunately, it's quite altered, as iron quite often tends to do, but you can see the granules sitting in there in a quartz or chert-rich matrix. But luckily, we've got the drill core, which is much fresher. Everything's better preserved there, so we could assess the thing a bit more geochemically and the petrography as well. So here's a polished slab from the surface outcrop, and these are thin sections that were made from the drill core. And as you see, you can even see some of the low angle cross bedding in the thin sections, and also you see these mud clasts sitting in there, and you can also see you're dealing with stacked beds, upward fining stacked beds. The cycles repeat. It goes from coarser granules to finer granules to shards to mud, and then it goes back. So we think you're dealing with a sort of a turbiditic depositional environment in some places, where these things, storm wave wash these things, and then they settle coarse to fine. And this is the petrography, and this is where this freaked me out a bit, because I was about 23 years old the first time I saw this. And I went on the optical microscope on the SEM, and wherever I looked in literature, I could not find anything that looks similar to this. So if you look, it's very weird granules. So you're dealing mostly with a chert core, and around this chert core, you get magnetite and calcite in the rims. And you can see it's not a typical granular iron formation where you see this typical concentric smooth rimming around the granules. This is very, very irregular. You see these little dome-like shapes all around it. So you wouldn't call this, when we talk about coated grains, you wouldn't call it an ooid. You would call it an oncoid, meaning it's got irregular rims. And oncoids are the definition for spherical stromatolites. So we interpret these to be microstromatolitic structures. Now, of course, in 2D causes a lot of confusion. So we published this last year in Geobiology, but we had a lot of issues with one of the reviewers, and he kept on getting confused with the petrography. So he would look at a picture like this, and then a picture like that, and he would talk about carbonate rosettes, and he would talk about stuff where we didn't know what he was talking about. But, I mean, if you look at this with a fresh eye, it can be a bit confusing. So there it looks like small granules clumped together, and there it looks like a big granule. But for me, when I looked at this, I said, that is a beautiful cross-section between one of these granules, and there you cut the rim. So you're looking more at a plan view in one of those. But, of course, it's 2D. 2D introduces a bias. So I was always thinking, how do you get around this? And you also get a little bit of minnesotite in the matrix. But what's interesting about this rock, if you look at the iron is, there's a very strong textural control on where you see the iron in this rock. If you look at a micritic banded iron formation, yes, you get bands. Iron rich, iron poor, iron rich, iron poor. You get massive iron formations where it's just iron all over the place. But the iron is all over the place. It's clearly been deposited in a system that got a lot of iron came in. This can't be the case here. I mean, if this was an iron-rich environment, the rock would just be full of iron. Clearly, this was a system where whatever formed these granules could control where the iron was going. So this is probably a much more iron-poor environment than what you see in a typical micritic iron formation. And we've got additional evidence for this, which I'll get to right now. So that's just to zoom in to say, my interpretation originally was that's a cross-section, and that's a bit more of a plan view. You're essentially sort of scraping on the edge of a granule in that view. So there's the geochemistry of this unit. A couple of interesting things there. What really stood out when it came to the geochemistry are two things. The first thing is the stable isotopes of the calcite, and this created a big petrographic challenge. If you look at the carbon isotopes in the calcite, it is very depleted. This carbon was sourced from organic carbon. Now, this is very typical for iron formations. If you look at siderites and anchorites in iron formations, they very commonly tend to have these highly depleted values. Now, it's easy to explain this. If you're in an environment where you're putting a lot of ferric, Fe3+ iron, into the sediment, and you're putting organic carbon with it, the two will react. You will oxidize the organic carbon, you'll reduce the iron to Fe2+, the produced CO2 and the Fe2 will combine, and you'll form an isotopically depleted iron-rich carbonate. But these are not iron-rich, they're calcite. And yet they have the same signature. So our interpretation was the iron was not responsible for oxidizing the organic carbon in this system. And it creates a lot of challenges, especially if you're sitting in the Mesoarchean, because there's not a lot of oxidants around. So if you have Fe3+, that was probably one of your bigger oxidants in diagenetic sedimentary processes. But in this case, we needed something else to explain the calcite, because the iron stays in magnetite. It doesn't really go into the calcite. You could say maybe because magnetite is partially reduced, that there's some partial reduction forming the CO2, and for some reason the iron doesn't go into the calcite. Problem is the calcite is not exclusively associated with the magnetite. So something else must be at play. And then here's another interesting one. We measured the iron isotope. So those little white blocks show where the material was drilled out to look and assess the iron isotopes. Now, iron isotopes work is you get a source of iron coming into a system. Now, generally, some assumptions go into this, but if you've got iron that's derived from mid-ocean ridge basalt, okay, getting leached and altered by hydrothermal fluids, and you push that ferrous Fe2 plus ion into a system, those isotopes will be very close to zero. A lot of experiments have been done, and they should be in bulk close to zero. Now, the only way to fractionate iron isotopes is by redox processes. So if you oxidize the iron, oxidation will preferentially include the heavier isotope. Reduction will preferentially include the lighter isotope. Of course, if you oxidize the entire pool, that signature just goes into the sediment like that. But that is not what we see in iron formations. We see a fractionation. We see the deeper iron formation return a heavy isotopic signature, and shallow iron formations retain a light signature. And why is that? Very easy. As the hydrothermal plume enters the sedimentary environment, you're partially oxidizing the pool as it moves closer to the coast. In deep water, the oxidation will have a lot of heavy iron to pull down, but the remaining pool in the water, the dissolved iron, becomes progressively lighter in its isotopes. So the oxidation takes the heavy iron, but it'll go from a positive signature to a zero signature, eventually to a negative signature. Now what we see here, and this is what made us think we're dealing with some sort of juxtaposition, that something like fish out of water, something from a different environment violently got washed into a calmer environment. Because if you look at the micritic iron formations there, the magnetites plot at zero. So that is a system where you already fractionated the iron plume coming in. The silicates are light. So there's already fractionation happening. So the iron in this iron formation, this is probably an iron formation sitting closer to the coast. The deeper iron formations were not preserved in this instance. And you can also see in the mineralogical facies, it fits. It fits that the mineralogy and the texture of these iron formations, they're more proximal to the coastline. However, now you go to the granular iron formations and you measure the magnetite in that, and it's heavy. So the iron that went into the granular iron formations did not come from the same pool as the iron that went into the micritic iron formations. The shallow water Archean ocean ambient iron was different from the deep water hydrothermal plume pushing into that continental shelf. So they're separate from each other. And if you look sedimentologically at the Wits and the Pongola, the iron does not deposit generally above wave base. All the iron-rich units are deep water below wave base deposits. So there's no evidence that those hydrothermal plumes were able to push dissolved iron into the photic zone. It's all sitting in the deep water. And if you look at hydrothermal plumes today, they do that. They reach an equilibrium with the ambient water, and they actually have a limited vertical extent. They have a top and they have a bottom. And the top generally sits fairly deep, not even in the photic zone. So we think this was a similar instance in this deposit. Now, the big thing here was that I thought the 2D petrography, clearly from the reviews we got, it was clear that this was confusing a lot of people. And then I went to a talk in 2010 in Hungary, in Budapest. I had attended a talk where people from Nexa were presenting their X-ray tomography and their neutron tomography, and I saw what they could do scanning in 3D. Problem you have, it's X-rays, so you need density contrast. Now, stromatolites have not been scanned in 3D, and there's a simple reason for that. The whole thing is carbonate. You've got a carbonate structure sitting in a carbonate matrix. It's all dolomite or all calcite. So there's no density contrast. So there's no way to do a 3D image of a traditional stromatolite. But then I thought about these and I realized, but all of the weird structures are accentuated by magnetite, and this sits in a chert matrix. So let's give it a go. So I contacted Nexa, I put in a proposal, and they said, well, come along, we'll do some preliminary scans, a proof of concept, and if you're happy, we'll take this further. Now, the catch with the micro XCT is that you need to make your sample very small because you essentially have an X-ray detector, and the resolution you get depends on how close you can get it to that detector. The smaller the sample, the closer to the detector you can go, the better resolution you get. So initially, the samples I took were too big. But from the scans, I already saw potential, and I thought, well, maybe this could work. So this was the first scan I did. So essentially, you do an X-ray, and you take these 2D slices. So you see every single petrographic thin section that could be made out of this block. Then the software goes, and it reconstitutes it into a 3D model. So that is sort of what that looks like. So you build up a 3D model. You can see there the granules sitting in a chert matrix, and there's an iron-rich mud unit right in the middle. So this was great because I could go through the different 2D slices, and even though the resolution was low, I could see a lot of the sedimentary features. So here we could see it even better that we couldn't see in the thin sections we had made. You could see there. Those granules are bigger, they get smaller, it becomes little shards, and it goes up into a mud. So the history of these things and their deposition at some point got quite violent. So it got washed up in a storm wave, and then as it settles back down in the deeper water, you get like a typical turbiditic sorting mechanism, where the coarser material settles out first, it goes to finer material, and these little shards shows that a lot of these iron-rich rims got broken up and broken off, and they will settle out last because they're finer and they've got the right dimensions to settle slower. And then beautiful, you can clearly see the upward fining process. So I thought, well, it's showing promise, but I'm not really seeing the granules. So I went back, wrote the proposal, it was approved, so we cut the blocks down to very, very small to get it really close to the detector. So I was a bit skeptical. I even spoke to a guy who specializes in granular iron formation based in London, and he said, don't waste your time. Micro CT scanning is a waste of time. This won't work. I don't know why he said that, but I ignored him anyway. And so I went and I did it. And I'll be honest with you guys, I did not expect these scans to come out as well as they did. So you can immediately see the difference here. You can see the grains are much clearly more visible, and you can see as well the 2D bias happening. You can see all those little grains aren't little grains. They're rim features of a bigger grain. So as you go through the 2D slices, you can see a bunch of small grains merging into a bigger grain. So I was luckily in this case, I mean a blind person will also eventually hit a dartboard, but luckily in this case I was correct in what was going on with regards to the 2D bias you see in different thin sections. But now of course, what's the point of just doing that? What the software can also do, it doesn't have to build a big block model. You can now go through a few 2D slices and tell the computer that density we have right there, which is the magnetite sitting on the rim. Let's take that, we extract this one granule, and we build a 3D model of one granule. And so that's what we did. So this is just a summary of what I could see already in 2D. What was also nice, because we see all these extra slices, we pick up features we missed. So for example, we see now some of these granules have got their rims missing. So that's a question. So if this thing is out of place, why is it out of place? Why don't the isotopes match up? And then we can see some of these things were affected by slightly more energetic sedimentary processes. Things got broken off, chipped off. All these small grains here are actually just the rim of one big grain. But another thing, and we still need to explain this, is the majority of the grains have the structure of a quartz center going into calcite, going into a magnetite rim. But we saw now a certain percentage, approximately 10% of the granules, have slightly more complicated interiors, where you get the calcite making up a larger proportion of the interior. That's when we saw you can't link the formation of the calcite to the formation of the magnetite. That's when we realized we need another oxidant in the system. So anyway, what about the 3D reconstruction? So what do these individual granules look like in 3D? And that is what they look like in 3D. And you can go through it, you can look at the internal structure, And as you can see, I'll point out certain features. The stuff that came through, I was really surprised at what we could see from these things. And they all look like this, sort of like an alien brain of some sort, or maybe a little river pebble that got acne or something. But there they are. And I mean, you can clearly see in these pictures, you're actually looking at a microscale stromatolite. That's identical to the stromatolites you see at macro scale, just at a microscale. So this is what these things look like as they're sitting in the rock. So it's very nice. You can pull these things out individually. You can see the orientation within the sample. There as well. These two are sitting sort of upright like this. So clearly these density currents were fairly high density. So these things couldn't all settle in a preferred orientation. It's a bit more random in the orientation. So I'll get back to why I'm showing quite so many of these. So if you notice, the cut going into this one shows a much more complicated internal structure to this one than compared to the previous two I showed you. And I'll also highlight what's going on here. So of course this one, is it this one? Let's see if as it comes around. Some of these things look weird in the sense that they look hollow on the inside, but what's happening where they do look hollow on the inside, it's just the magnetite rim that got broken off, and you're essentially looking into the chert, and the chert's been extracted. You're only looking at the magnetite in these images. And then again, here's two grains sitting within the block, and now you see these are sitting at a different orientation. These two are sitting more flat, whereas the others are more vertical. So these are the observations we saw in 3D, just to highlight them. And we see in 3D, these things are indeed these little microdomes sitting on the rim of these granules. We believe these are biological structures. We've shown it to microbiologists, and they're also convinced these are biological structures. You won't form them in another way. So it's essentially a bacteria living on the rim of the granule, growing outwards, precipitating probably ferric oxyhydroxide as it goes along, and this essentially builds these little microdomal structures. Of course, why do they grow out in every possible direction? Simple, because they're in shallow water. Every now and again, a wave or some current reorientates them, and the bacteria has to start all over again. Then they grow up, and then it gets reorientated, and it grows up again. And there's quite a bit of evidence for this process. Okay, then again, the multiple granule orientations, probably indicative of the sedimentary transport that took it from where it was formed to where we now see it preserved in the deeper water. And then smoothed surfaces. I mean, these things were moved. So that surface right there has essentially been scraped or scratched off by a sedimentary movement, indicating that they were moving every now and again as they were forming. Again there, smoothed surface, something scratched off some of these domes in that specific part of the grain. Domes broken off. So there you can see domes had been formed, but then the movement in some instances broke the dome off. So some of them are opened up, and you can see the internal structure of the dome exposed in that specific surface. Again, domes getting broken off, and here's an entire section of the rim that also got broken or ripped off the outside of this granule. And this is where it gets interesting. So we actually think that in some instances you had two generations of granule formation, that some of these granules started forming, and then what happened is some chert coated it again, because in the Archean probably these environments were quite rich in chert, and chert was precipitating out of that Archean ocean water quite often. So the process essentially repeated around it. So it's like a Kinder Joy egg, and that's the toy. And there you can see another orientation of that. So what we saw from the 3D scans is 80%, we think 80% of what we proposed in the original publication is correct, but there's now that 20% of more complexity that we also need to build into our depositional model for these granules. So this is the model we published last year in Geobiology. So essentially what we say is, if you look at the banded iron formation, you're only preserving a certain section of it. You're looking at the more proximal iron formation. That's why you see highly fractionated iron isotopes. If you look at the granular iron formation, those iron isotopes are essentially reset. That iron is coming from a different environment. Also, if you look at the abundance of different sedimentary structures in the surface outcrop, it shows there was wave interaction with this, and we think essentially at some point a storm wave came and washed these things down into slightly deeper water, juxtaposing it with the deeper water micritic iron formations. That's why you see these stacked beds, and that's why you see 3 stacked beds back into a biff, and then another stacked bed in there. So the only reason we were able to find this is in some instances it essentially got washed into a chemical sedimentary nursery, as it were. Whereas where it was originally formed, that would have been the first thing to go through erosion. And we think that as well. You see these domes growing out in every possible direction because in the environment where they grew, the granules got reorientated every now and again, meaning these little microstromatolites had to start again. And that's what they do. If you look at the Campbell Rand dolomites, at different stratigraphic levels, you just see the stromatolites adapting. As you go through a transgressive sequence, you see them change to match the depth of the water. So these things were probably quite resilient. But this is the first time in this, because you see in the Phanerozoic in Egypt, you can see iron oxidizing bacteria grew stromatolites. Now we see this for the first time in the Archean. So this is the first time you can see biological morphology connected to iron precipitation. And there's a large school of people that believe the majority of the iron and iron formations were put there by iron oxidizing bacteria. Because why wouldn't they if there was that much chow around, you know, breathing iron? If there's a lot of it, then it will live there. So what extra value did the 3D constructions add? Well, my first thing, I didn't put it on the slide, but I just think it looks really cool. And sometimes that's worth doing something if it really looks cool. You can't always buy a functional car. Sometimes you have to buy a cool car. Sometimes. You'll probably not drive it very long, especially if it's out of maintenance plan. But still, everybody at some point wants a cool car. So, or at least I would. So what's very nice about this, it takes that 2D, and I think a lot of time people forget, and this is where in geometallurgy, I don't like speaking about it too often, but in geometallurgy, you immediately become aware of the inherent bias in doing 2D petrography. So for example, if you do a 2-dimensional SEM scan and you use that to do a grain size distribution, it's always smaller than when you sieve or you do a Malvern laser sizer. Because you never ever cut a grain through a perfect diameter that you get its maximum size. So 2D introduces a lot of bias. In this instance, the 3D tomography completely removes that bias. And you can really see what these things are about and what they look like. So what I thought were microdomes and microstromatolites, in 3D they look even more like microdomes and microstromatolites. What's also nice is I didn't expect to see the level of detail where you can see where the sedimentary processes broke off and smoothed over the rims of these granules. So I was very pleasantly surprised by the level of detail we got from the 3D scans. Now, of course, it confirmed a lot of stuff, but there's a lot of stuff we still need to figure out that was brought forward. So, for example, we still need to find someone to tell us if they can tell us a bit more about the classification of these structures, more from a microbiological point of view. These compound grains or composite grains, we see a granule sitting inside a granule. We still need to figure out the kinks about what process would have formed that. And we're now definitely confirmed that you can't link the organic carbon oxidation to iron reduction. So we need an oxidant. Nitrate, some sort of methanogenesis, could be. It's just difficult because these processes don't really leave a lot of evidence. People also don't like nitrate because you can't really have nitrate without free molecular oxygen. And you get some people, if you just mention free molecular oxygen before 2.4 billion years, their eyes go back and they start foaming at the mouths or something. So some people are quite militant about surface environments in the early Earth. So yeah, these are some interesting things we saw about this. And I think it's a fascinating unit, and it gave us a very unique opportunity to use a technique that 90% of the time you would not be able to use in this field of study. So thank you for your time. Is there any questions?
Thank you, Bertus, for that excellent and very interesting talk. Lawrence.
So in conventional iron formations, normally people talk about upwelling of ferrous iron and you oxidize it to ferric iron and you precipitate out because the
Yeah.
solubility of the iron is reduced.
Yeah.
But what you're suggesting is that this was maybe all biogenic because it's all essentially ferrous iron 2+, which is precipitating. So are you suggesting...
No, ferric. We think the original product was ferric iron because it's magnetite. Yeah.
So how do you make magnetite if it's all ferric iron?
Well, there's a couple of ways you could do that. So, for example, when you form a ferric oxyhydroxide, if there's still some ambient ferrous iron, it's possible to react that directly in the sediment, that it takes up some of the Fe2+ to form magnetite. But it could also be that some of the organic carbon makes that happen, that there's just enough organic carbon to reduce some of that Fe3+ to form the magnetite. That's another thing about iron formations in the Precambrian. If you actually go look at it in drill core, the most common mineral you see throughout is magnetite, followed by iron-rich carbonates. Hematite and iron-rich silicates are not that common. So there's definitely a lot of post-depositional reduction happening. Post-depositional reduction. Yeah.
It was all supposed to have been ferric iron to start off with. How do you explain that?
Well, it's the sediment. It's what goes into the sediment. So even if you do oxidize to ferric iron, the iron isotope shows there's not enough oxidants to oxidize all the Fe2+. So even if you're putting Fe3+ into the sediment, there's still Fe2+ in the system. Not just that, if you look at the carbon isotopes of the carbonate, there was a lot of organic carbon going into the system as well. So if you just look at what ingredients go into the sediment, hematite doesn't stand much of a chance to be preserved in the first place, even though you put ferric oxyhydroxide in there. We do see hematite though, and that's when you go to iron formations where you're sitting at the maximum point of transgression. We're talking about the bit of the iron formation that was put in the deepest possible water as far away from the coast as possible. There you will see hematite preserved. And it's primary. I'm talking here, there's no evidence of a post-depositional reaction to form that hematite. You will see thin beds of hematite. And we think essentially you're either in a system that's deep enough or far enough away from the coast that not that much organic carbon goes in, but we also think it's because the plumes, they've got a top. But in today's modern oceans, these plumes also have a bottom. So we actually think you're again sitting in a hematite nursery, where that Fe2+ that's still in the ocean is not at the sediment-water interface. So there's a slightly higher probability of preserving hematite. It's about preservation. It's about what goes into the sediment. But it's very difficult. I mean, we're essentially, we're given a puzzle and we have to break it down and try and see where it came from. And that's always an inherent challenge when you're dealing with very old sediment, is to try and take what you see and take it back to what was originally going in. And there's definitely margins for interpretation and error. Yeah, Andrea.
Bertus, your grains won't be shallow water.
Yeah.
Close to the continent.
No, probably not close to the continent. That's something, sorry, I didn't mention that. There's no aluminium in these things. So even though they're in shallow water, they probably formed from the reworking of a chemical precipitate. So you're probably looking at a paleohigh of some sort, similar to what you would see in some carbonate platforms, that you've got a paleohigh putting it, or there's not sediment, but that's not the case. We know in the Wits and the Mazon, there was always detritus going into the system. Even the iron formations tend to be quite dirty. So we think you're looking at some sort of isolated paleohigh platform that occurred in the basin, because there's no detrital component to these things. So we think it's chemical precipitates getting reworked by the waves. And you do see evidence for that chemical precipitates can get reworked into peloids or nodules.
So basically your iron isotopes are
Yeah.
telling us something about shallow water, is that right?
In general, yes. Yeah, at least, but I always tell people, be very careful, because people will go to a thin section from the Hammersley Basin in the Brockman Iron Formation. In two thin sections, they'll find nano-inclusions of granulite in hematite, and they'll say, therefore, all BIFs were originally granulite. And no, it doesn't work like that. I can tell you that in the Mazon at that point of time, there was a paleohigh, and it appears that the shallow ambient iron and the deep water iron were two decoupled systems at that time. I'm not going to use that to tell you what the Earth was like at 2.84 billion years, because we don't know the extent of that basin, how connected it was to a global ocean. And I think a lot of early Earth geologists need a reality check.
Bertus, you ended with some
prior to the GOE.
Yes.
Yeah.
In this shallow water environment.
Yeah.
But just a couple of months ago, NRCI published a paper in Chemical Geology concerning oolites from the underlying Suzy formation under the Mazon.
Yeah.
And these oolites are clearly shallow water coated grains, carbonate, and from the rare earth element signatures of the oolites, there is in fact a very slight serial anomaly, which indicates the possibility that there was oxygen present.
Now,
in that shallow
I would be very skeptical of that study. Was that surface or borehole samples? Any study like that on surface samples, I wouldn't trust. We've got a paper coming out now in Geochemistry, because they published a paper in Nature a few years ago where they saw chromium isotope fractionation in the Suzy and said there was free oxygen. If you compare the surface samples to the borehole samples, you see the chromium isotope fractionation happen in the last few thousand years at the surface. So one has to be careful, because cerium anomalies are generally completely lacking up to the point when you get to the Kuchas and the Kalahari manganese field, generally. I've seen, when you look at 100 samples, you'll see 3 or 4 slight cerium anomalies. So I still have to read that paper though. But I do, if you look at the bigger mass of evidence in the Wits Mazon, I think there must have been at least micro levels, like 8 or 9 or 10 micromolar free oxygen. You see proximal distal manganese iron in the azomane. If you're in the shallow part of the azomane, there's manganese. If you're in the deep part, there isn't. The only way to do that is a redox control. The only way to oxidize manganese is with some free molecular oxygen. If you look at the contorted bed, all the iron sits below wave base. So there's no evidence that the iron got to a point where you could get completely anoxygenic phototrophic bacteria. But you do get deep water bacteria that can do it, but they need, and we get back to this number again and again, 8 micromolars of free oxygen. So I think there's an abundance of evidence in the Wits Mazon that there was some free molecular oxygen. It's very easy. Why do we see the mass-independent sulfur fractionation? Easy. There was oxygen, but it stayed in the ocean. There was just so many things using up the oxygen, it couldn't build up in the atmosphere. So I always wonder why people are so militant. They see atmospheric evidence for no oxygen, and therefore they believe there was no oxygen anywhere. You know, they'll do bacterial phylogenies and use the phylogenetic charts to say, look at this phylogeny. Cyanobacteria couldn't have evolved before the GOE. Then the next talk, it's another phylogenetic chart where the person says, oh, this thing has an error of plus minus 400 million years on it. So that's why I say a lot of these early Earth people need a reality check. They need to realize that sometimes, even if it's an isolated instance, that tells us something about the Earth. I don't know why they go to one outcrop and suddenly now they want to say this is how the whole Earth was. I mean, there's a 1 million year old banded iron formation in Greece.
Sounds like something we should discuss over a beer.
Yeah, sorry. I'm going on too long here.
Let's go for a beer after and have a good debate about that. Are there any other short questions? Okay, well, Bertus, thank you once again for a very informative